In section 8.3, we're estimating the value of a population proportion from a single sample. Since we've already covered estimating population mean, I think this will actually be a little bit easier. We don't have to worry about critical value t because we don't have such variability. With a quantitative measurement, when you take a small sample, you tend to underestimate the value of s. And so to make sure that your margin of error is big enough, you need to inflate your critical value, and that's what t is all about. So I talked about that in this video about the student's t distribution. But in this situation, all we have is a population proportion, and we don't have such high variability. Here's what I mean. In this situation, we have a very small sample taken from a population with 60% success rate. So suppose a candidate won with 60% of the vote, and we just ask 5 people at a time how they voted. So drawing one sample, we can see we get 80% of that sample, 4 out of 5 voted for that candidate. So not a very good estimate, that's off by 20%, but we'd expect to see a good amount of variability here because we're only asking 5 people. However, most of the time we do land on that 60%. Well, maybe not most of the time, but more than any other outcome. And most of the time we're kind of within a certain range of that 60%. So there would be a really high variability of this distribution, but if I were to continue that on, I would have approximately a normal distribution. However, it doesn't quite meet the requirements of sampling distributions. So that's really the issue here is I do see a lot of variability, but I haven't met the requirement. So if you do meet this requirement, you don't even really run into that issue of such high variability. As long as you have n times p times 1 minus p at least 10, which for a 50-50 sample would be 40. So let me show you what I mean. 40 times p of 0.5 times 1 minus p of 0.5, that would hit your mark of 10. And as you skew more from that, you need to have a higher value of m. So when I did 5, that wasn't big enough. This needs to be at least 10. If I bump it up to 40, that gets me close to 10, but not quite there. So for a 60-40, I'm going to have to go all the way up to 42. And when something's very skewed, for example, with a 0.95 times a 0.05, imagine trying to estimate the value of this parameter if you have a small sample. This group is in the minority with only 5% of the population. If you sample 5 people, you're probably most likely not even going to find someone in that category. So here, if I try sample size of 40, I'm much too small to be able to represent that minority. In this situation, I might have to go much higher. Even at 100, I don't reach that amount. Let's see, I would need to be probably around 500, 600, something like that. Okay, that's plenty big. Okay, it looks like a little over 200. We're going to reach that value of 10. So 210 doesn't quite make it. 211 makes it for that 95%, 5% split. All right, so going back to my example where it's 60-40, let's bump this sample size up to 42. So we've just met the requirement. We've just gotten over that value of 10 there. And let's take 10,000 samples from that. So here we can see a lot more defined, that bell curve that we like to see. 60% is here in the middle with the highest probable outcome. Not necessarily the majority. It's not more than half the time or anything like that, but it's the most probable outcome with a very predictable curve. And if we wanted to be confident with a 95% confidence level, we could look at that kind of that middle percentage. We could look at that middle 95% and come up with kind of a margin of error for where we think that parameter would be. So that's what it's all about with population proportion. You can see all we really do is we use a sampling distribution, but instead of using a known proportion, we use our sample proportion to determine that margin of, or that standard error. And that standard error is a measurement of how far is it to the first standard deviation? So when you kind of flatten out on the side of that, about halfway down. And then that's a measure of standard deviation size, and z is the number of standard deviations we want to go. So if I want to calculate this, I can do this pretty easily with staplets, and I will do that in the next video.